Okay, we're going to look at nuclear magnetic spectroscopy, and we're going to be looking at carbon and hydrogen and how they're put together. With NMR, we actually get to look at the carbon structure and look at how hydrogens are attached. This is the most important tool we have for figuring out what the structure is. We use IR and mass spec in combination with this, and then we become quite educated about what the structure of an unknown compound is. So what does NMR do? When we look at proton NMR, we see the electrical environment of hydrogens, and we can detect how many hydrogen neighbors that a particular hydrogen might have. In carbon-13, we see the electrical environment of carbon, and we can also, with a certain type of C13 NMR, determine how many hydrogens are attached to it. Well, nuclei have spin, and what we find is that the spin of the odd mass nuclei are very useful when we're trying to detect them and look at their magnetic environment. When you put a nucleus in a magnetic environment, what happens is the nucleus lines up either with or against the magnet that you're applying to it. That gives two different energies because spin aligned is lower energy than spin against. We call that spin parallel or spin anti-parallel. So if I look at this, as I increase the magnetic field, what happens is the difference between these two states of either being aligned with or aligned against the magnetic field increases. The energy of this transition is about the same as the energy of radio waves. And so we can apply a magnetic field to hydrogens and then with radio frequency make them go from low energy state up to high energy state. Okay, nuclei that are active in NMR are hydrogen with a single proton and no neutrons, and carbon-13 because they have odd mass nuclei. There are others that we can use in NMR, for instance, fluorine-19 and even nitrogen because it has 7 protons only, which is odd, and we can detect it in certain circumstances. Can be done, but the ones that we find useful really are proton NMR and C13 NMR. The others are kind of used by people under unique circumstances. Deuterium and carbon-12 are both invisible in NMR. So we have to keep that in mind when we're looking at what we're doing and understanding some of the things that we do. In order to understand what we're looking at in a proton NMR, you have to understand how the energy of flipping the nuclear spin occurs. We know that when we apply a magnetic field, it causes the nuclei to spin align or spin anti-parallel. And the difference between those states can be it will be the same energy as a radio wave. But what we find is not all nuclei are the same, respond the same to the magnetic field because the electrons around a nucleus spin in that magnetic field and cause a change in what the nucleus detects as the external magnetic field. So, a dense electron cloud is going to shield the nucleus from the external magnetic field, and the energy of flipping the spin is very small. Likewise, a thin electron cloud allows the nucleus to be kind of naked in that magnetic field, and so then it takes a lot of energy to flip the spin. And we call this deshielded. Here are two examples of NMRs. On the top, we have a proton NMR, and on the bottom, we have a carbon-13 NMR. We are this of the same molecule. We're looking at methyl acetate in both circumstances. Here we have two different kinds of protons. This set of protons is directly attached to an oxygen that's electron withdrawing, and it pulls the electrons away. And so what we see is, because it has an electron withdrawing group on it, it deshields it and pulls its absorbance down, farther down the field. And we say it's downfield or deshielded. Here we have a proton on a methyl group that's attached to a carbonyl. So in this circumstance, the electrons are not being pulled off it as much as for this one. As a result, we say it's shielded, or we might say it's upfield. In every sample, we put a standard called tetramethylsilane, which has silicon surrounded by 4 methyl groups. Silicon is less electron withdrawing than carbon, so it essentially pushes electrons onto the hydrogens in the methyl groups. This standard we always give as a 0 part per million, and we compare our absorbances to this standard. The same standard is used in both carbon-13 as in proton NMR, and you can see there's a TMS peak right here. In methyl acetate, we have 1, 2, 3 different carbons. This one is right here. This methyl group is more shielded and is right down here, this blue one. This carbon is right there in that carbonyl, and so it's really deshielded, and that's right down here. So the left side of the spectrum is deshielded or downfield. The right side of the spectrum is shielded or upfield. The peaks that we see, we call them either peaks or lines or absorbances. They are listed in here in parts on the spectrum in parts per million. So here on this proton NMR, this is at 2 parts per million, and this is about 3.7 parts per million. The carbon-13 part chemical shift numbers are very different, and they go from 0 up to past 200 parts per million. You can see there's a lot more noise in a C13 NMR, and that's because there's a lot of protons with one mass of 1 in any organic molecule. But in any organic molecule, there's only isolated cases of carbon-13. It's at about 1% abundance. And so to detect it, we have a lot more noise, and you can see it's a little bit, the peaks are weaker with regards to the noise. When we're looking at proton NMR, we see a lot of different information. The first information is the electrical environment, whether or not the electrons are shielding it or deshielding it. And that tells us what kind of groups are attached to the carbons. It tells us how many protons we have, because the size of the peak, the area under the curve, is proportional to the number of protons making that peak. And we call that integration. It also tells me how many neighboring protons a particular set of protons might have, because other protons are little magnets, and they change the strength of the magnetic field of their neighbors. And we call that coupling or splitting. Okay, so for shielded nuclei, what do we see, those are going to be protons that are attached to a group of atoms or atoms that are not electronegative. So we see shielded nuclei in alkyl groups and tetramethylsilane. Deshielded groups are where you have electronegative atoms attached to carbons that the hydrogens are attached to. So a hydrogen on a carbon that has an oxygen attached would be very deshielded. So just to let you know that there's two ways to construct an NMR. One, you could have a steady magnetic field and vary your radio wave to find out how much energy it takes to flip each of them. Or what you can do is hold your radio frequency steady and then vary your magnetic field. And since the magnet is an electromagnet, it's very easy to change the magnetic field. And so the instruments are based on that, where you have a single radio wave always being shined on the sample, and then you take the magnetic field and you ramp it up until you get to the zero of TMS. So if we look at this, down here we have a weak magnetic field applied to cause the nuclei to shift in a particular radio frequency. And up here we have a large magnetic field needed to cause the nuclei to resonate or be increased in energy by the radio frequency. We call when a nucleus is flipping in the magnetic field because it's absorbing radio waves, we call it resonance. So downfield, that's where you have the electrons being pulled away from the nucleus. Upfield, they're being pushed on the nucleus. And we express this in terms of parts per million, which we'll go into how that is calculated in just a minute. Okay, the chemical shift is measured in parts per million, or we use the symbol del with TMS as a standard, and TMS is always a standard. And because the amount of energy that is required to make the nuclei flip depends on the magnetic field, and some magnetic fields have a huge magnet on some machines, and some machines have smaller magnets. What we do is to make the chemical shift independent of the machine is we take the hertz, that's the magnetic field strength that is required to cause the machine, cause a proton to resonate, minus the hertz of the resonance of the TMS peak. That difference is then divided by the total magnetic strength of the machine's magnet. So if you look at TMS, because the strength of the magnetic field there is the maximum of the machine, you take the hertz of the TMS divided by the hertz of the machine and you get 0. Whereas with something else that, let's say, is at 1 part per million, it's going to have a much lower resonance, hertz of resonance, lower field needed to cause it to resonate, and so that you get a positive number then. This is tetramethylsilane, 4 methyl groups on a silicon. And because silicon is less electronegative, it pushes electrons onto the hydrogens in this and on the carbon. And that is our standard that is used in both carbon-13 and proton NMR. So here's an example of shielding and deshielding. Here's our TMS at 0. And then what we have here is just methane. So right here at 1 parts per million, we find methane. You put a chlorine on and look, it shifts it downfield. You put 2 on, it shifts it down even farther. You put 3 on, it shifts it even farther. And that's demonstrating how electron withdrawing shifts the peak downfield or to higher parts per million. Here's an example of some organic molecules. Dimethyl ether has an absorbance at about 3.3 parts per million. Dioxane, even though it's very similar to dimethyl ether, it still has 2 oxygens in the molecule, and even though this oxygen is somewhat farther away from this, it still affects it. And so it's still pulling on the electrons through there. And so you see the absorbance of those protons being shifted downfield. And then look at formaldehyde. Its peak is way down here. Very deshielded. However, pi systems are not deshielding through an electron withdrawing method. What it is doing is that the pi electrons are circulating and causing the magnetic field to be stronger at the nucleus. In an alkene, you have a pi bond, and when that pi bond, the way it's oriented, when you apply the magnetic field to the pi electrons, they circulate in a way that causes the magnetic field of the protons to be increased. And so it's like it's been deshielded because the effective nuclear, it's like the electrons have been pulled away because the nuclei can feel the magnetic field as being stronger. So we say that alkenes deshield the protons. The benzene pi system does a very similar system because the benzene have the electrons in a pi system above and below where the protons are. When you put the benzene ring in the magnetic field, they circulate in such a way that they cause the magnetic field at the protons outside the ring to be much stronger. And so what you see is the proton out there thinking the magnetic field is very large indeed. It's like it has no electrons around it. It's equivalent to it, even though there's still electrons around those hydrogens. And so what we say is that aromatic rings are very deshielding. Here's an example of where you would see them. Here is ethene, and right down there, ethylene has an absorbance for its protons at about 5.2. Benzene has an absorbance for its protons at about 7.3. And you can see that this is very deshielded, even though there's nothing electron withdrawing on it. And an aromatic ring is even more deshielding, even though there's nothing electronegative on it. Alkynes have their electrons circulate in a different way. They circulate in a way that is perpendicular to the sigma bond. And so the magnetic field that is made looks like this. And that actually enhances the magnetic field at the nucleus. And it decreases the magnetic field at the nucleus of the proton. And so we actually find alkynes are shielding much more than the alkenes are. So here is a comparison. Here is acetylene at about 2.6. Here's ethylene at about 5.2 and benzene at about 7.3. You can see that an acetylene is shielded in comparison to an ethylene. Okay, so this is what you learned. More electronegative groups give greater deshielding, which gives a larger del value, or parts per million. Double bond and aromatic pi systems cause a large shift downfield, and triple bond pi systems, they do not shield as much, and so they're almost down where the alkyl groups are. They're somewhat shielded. These are the chemical shifts that I want you to know. Here's an aldehyde proton, and I usually say the aldehydes are around 10, but these are broad ranges. You have to always look outside the area that you predict it to be, because other substituents can have unpredictable effects sometimes. The aromatic absorption, I usually say, is around 7. The vinyl absorption is, I'd say, around 5 or 5.5. Here's a hydrogen that's on a carbon that has an oxygen attached. It's at about, I'd say, 3.5. A hydrogen that is alpha to a carbonyl, that's at about 2.5. A benzyl hydrogen, also, it's at about 2.5. An allylic hydrogen, I'm going to say that's close to 2.5 also. And then your alkyl groups are way down here, right centered, are all about 1. The quaternary carbon, tertiary hydrogens, and the are more shielded, and the primary carbons are less shielded. And then any electron withdrawing groups that are a few carbons away can still cause your hydrogens to be somewhat deshielded and a little bit higher than 1. Also know that the acetylenic hydrogens are in the 2 to 3 range, so let's just say 2.5. Alcohol groups, we can say they're in the 2 to 4.5 range, but I've seen them outside that. They're very unpredictable because of hydrogen bonding. So always take that absorption with a little grain of salt. Acid protons are off field, as we say, or you can see they're higher than 10, or off scale is what we say. And also the nitrogen hydrogens are deshielded because they're on a nitrogen, which is somewhat electron withdrawing. Yes, I'll be there in a minute. And so you can see that these are all broad peaks because they can hydrogen bond. So when you see a broad peak in NMR, always think protic. And then what you can do is add a little deuterium oxide, and the exchange with this deuterated water actually causes the peak to disappear because a deuterium replaces this and the peak goes away. And so you have 2 ways of recognizing protic hydrogens. 1, that they're broad. 2, you can add deuterium oxide and it removes the peak. So now looking at these, I want you to identify which hydrogen, the one that stuck out on a bond, I'm identifying it that way, which hydrogen would have an absorbance that is more downfield. Remember, downfield means that you have a larger part per million, and so that it's more deshielded. Okay, for this first problem, which one is going to be more downfield? This has a chlorine and this has 2 chlorines. Because 2 chlorines is more electron withdrawing, this hydrogen will be more downfield. Its number of parts per million will be higher. In this structure, we have a tertiary hydrogen, and here we have a primary hydrogen. Which one's going to be more downfield? The tertiary hydrogen will, because carbons are more electron withdrawing, and we see this slightly downfield. Now the absorbance of this hydrogen probably would be about 0.8 or 0.9. The absorbance of this hydrogen would be only slightly higher at, let's say, maybe 1.3 or 1.2. So there's a very small difference, but you can detect it, you can see it. this group, a hydrogen on the carbonyl. The carbonyl has oxygen on it withdrawing electrons, but the pi system deshields the hydrogens also. Here you have the hydrogen on the oxygen directly. Because we have the pi bond attached here, this is more deshielding, and we see this around 10, and we see this at around, let's say maybe 3.5 parts per million. If I look at this vinyl hydrogen has a pi system on it, which deshields the proton. This hydrogen has an aromatic ring on it, which deshields the protons. But aromatic rings are much stronger deshielders, so what happens is that the aromatic ring gives you a more downfield shift.